before, but it helped us get where we're at. So we can still use this to look at, to kind of show that there could be some relationship between the mantle, movement of the mantle, and the surface plate. So I have this material on top here. This is our surface plate, our mantle material. This is made of foam, beads, and paraffin wax. And this is corn syrup. Yep. And it has a high viscosity of I think 1.3, 1.4, or no, it's the density. Viscosity is like 2,000 to 3,000 or something. If we turn this crank, we can simulate the convection current and then see what happens to the surface plate. So what I'll do is I'll just turn this at some particular speed. Notice how it's all even right along here, okay? And we can turn this at some speed, and then what did we notice? We can ask the students what they noticed, and during the convection and even afterwards, there's a lot going on. We noticed that the material, when we spun it, started to go down, and then it started to kind of fold up and go on top of itself, and this and that. So it folded and thickened, and it started moving downward. So it's even forced downward too, because of this cell we made. And then when we stop that, there's no more force pushing into it. So now it wants to go through this isostasy. It's isostatic readjustment. And it starts to rise, and gravity wants to pull everything out this way, and there's no real structure here to stop it. If I put some blocks, wood blocks here, it can maybe simulate the, like a liquefied material, so when it opens up, it can get harder, add some back structure to it. So it wouldn't fall out that fast, and then we might be able to see this rebound a lot better. But now that it's in isostasis, it's in equilibrium, however you want to say it. Then if we look at the crust, or surface plate here, notice that it's low here, it gets higher here, and it gets low here. We can also look at here. It also gets, it goes deeper here. And we can talk about how mountains, we find that mountains have, deeper, we call them weird roots, and how it's there towards the end of the topography goes down. And as the mountain erodes, that kind of moves up, so it's in equilibrium. It tries to be in equilibrium all the time. So that's another concept to kind of cover with this. And then we can have students experiment with this and try different types of materials, different speeds, different dimensions, the heights and viscosities, and compress them or even spread them apart, going the opposite way. You can see what happens. If we go too slow, this is probably not the right scale by going this slow, but if we go fast, then it might scale up to what the Earth, what we would see in the Earth. And that's something that we would want to check out when we're using the model. Is the scaling proper? Is it scaling right? Is it scaling with viscosity, length, time, density? Because those all can be, you can use those all together for dimensional analysis to figure out if it's correct. And what you would need, like if you have a lower viscosity, then you might need to move this faster. So in Griggs' model, he had a high viscosity, so I think he moved it slower.